Welcome to this explainer. We're diving straight into a highly dynamic, almost hidden part of our ecosystem, soil water. Water moves through soil as a solid, liquid, and vapor. Understanding exactly how and why it moves is absolutely crucial if we want to get land management and agriculture right. We're going to break down the strict mechanics of flow, the equations that govern it, and ultimately why managing all this through drainage solutions is such a big deal. Let's get into it.
Okay, here is our roadmap for today. We'll start with the concept of flow, compare saturated and unsaturated conditions, look at vapor movement, dive into infiltration and percolation, and wrap up with drainage solutions and why they matter so much. Starting right off with the concept of flow, let's look at driving forces and conductivity. Now, we begin by breaking down how liquid water actually moves thanks to a pressure gradient. It all comes down to a foundational equation. Q equals CdK. Basically, this proves that water movement through soil is strictly proportional to the driving force and the soil's conductivity. Q is our flow velocity. D is that driving force, which for water is a pressure gradient. And K? That's the conductivity of the medium itself.
This whole relationship is formalized beautifully by Darcy's law. It establishes that the velocity of flow through a porous medium is directly proportional to the force causing the flow and to the hydraulic conductivity. So under saturated conditions where the pores are completely filled up, this flow is dictated by hydraulic force, usually just gravity, and how easily those soil pores let the water move.
But what happens when we zoom in on those individual pores? That brings us to Poiseuille's law, which reveals the mechanics inside narrow tubes. It tells us the rate of flow is proportional to the pressure, sure, but here's the crazy part. It's proportional to the fourth power of the tube's radius. That means pore radius has a massive exponential impact on how fast water flows. Oh, and it's inversely proportional to viscosity. So as water gets colder and thicker, it literally slows down as it tries to push through these microscopic spaces. Let's build on this and directly compare saturated and unsaturated flow.
There is a really stark contrast here when we look at the actual moisture state of the soil pores. In saturated flow, like right after a heavy rain, most pores are completely filled. The soil water is at 0 bar tension and the driving force is positive pressure. But unsaturated flow? Totally different story. Many pores aren't filled, the soil water sits at a higher tension, and that driving force completely flips to a negative pressure potential. And here's a crucial detail. Plants actually take up water that's mostly held under these unsaturated conditions because a lot of the water in a fully saturated state just isn't available to them.
Now this is a truly fascinating surprise. We actually see a complete reversal in hydraulic conductivity. When saturated, water flows through large, continuous macropores, so sand flows fastest, then loam, and clay is the slowest. But under unsaturated conditions, where it's at a potential of negative 0.1 bar or below, only micropores handle the water. Because of that, the whole sequence completely flips. Suddenly, clay takes the lead with the highest hydraulic conductivity, followed by loams, and sand comes in dead last. Pretty wild, right?
Water doesn't just move as a liquid, though. Let's shift gears to vapor movement in soils.
Even though vapor moves internally in really small volumes, its mechanics are super precise. Vapor always moves from zones of high vapor pressure, where the air is nearly 100% saturated, to zones of lower pressure. And temperature is a huge trigger here. If a patch of moist soil cools down, its vapor pressure drops, physically pulling water vapor toward that cooler spot. On top of that, electrolytes and applied fertilizers will locally reduce vapor pressure. This creates a gradient that actually pulls vapor right toward those pockets of high salt and fertilizer, making nutrients available to the plants. In a drought, this vapor movement is absolutely crucial for keeping drought-resistant desert plants alive.
Okay, so how does surface water actually enter and travel down the soil profile? That brings us to infiltration and percolation.
The first step in that journey is infiltration. This is the entry of water right at the soil-air interface. It's incredibly important, practically speaking, because it dictates exactly how much rain or irrigation water gets into the soil versus how much just overflows as runoff. In a dry soil, regardless of its texture, this infiltration rate starts off extremely high. But then it drops exponentially over time before finally settling into a steady rate.
Once the water actually makes it inside, percolation takes over. This is the downward movement through the bulk mass of the soil. It happens when water is under pressure or when tension is smaller than about half an atmosphere. Now, because evaporation and plant transpiration use up a lot of the entering water, percolation naturally tapers off the deeper you go. So the vast majority of percolation is happening right up in the top few centimeters, moving downward primarily through macropores in coarser textured soils.
But we have to ask the inevitable question, right? What happens when water arrives way faster than that soil-air interface can absorb it? When rainfall exceeds the soil's infiltratability, or the storage capacity is just maxed out, you get excess water pooling at the surface. And this ponding effect, this prolonged saturation, leads to some really serious problems.
That ponding leads us directly into our next topic, practical soil drainage solutions.
When you're dealing with low soil permeability, humid climates, or shallow water tables, subsurface drainage problems pop up fast. To fight this, we use specific underground networks to physically channel excess water away. First, there's mole drainage, which involves pulling a pointed plug to create a 7 to 10 centimeter cylindrical channel right in the soil. It's easy, but it tends to clog after a few years. Then we have perforated plastic pipe. This is the big one. It makes up about 90% of all underground drain installations today. Water simply moves through the perforations to an outlet ditch. Finally, there's the older clay tile system, using 30 to 40 centimeter individual pipes buried in a ditch with straw or gravel. It works, but high installation costs make it pretty rare nowadays.
To wrap up, let's look at why soil drainage matters so much. Why is preventing continuous soil saturation so vital?
Well, first off, proper drainage ensures we avoid continuous soil saturation, which has drastic negative effects on crop growth. It physically stops the development of certain diseases and parasites that just love wet conditions. Plus, poor drainage is actually a primary cause for the development of salt-affected soils. By managing the water table with proper drainage, we eliminate the physical limits that a high water table places on deep root penetration. We're literally giving the roots room to breathe and grow.
Speaking of breathing, soil saturation physically blocks gaseous exchange. This leads to oxygen deficiency and lets carbon dioxide build up to completely toxic levels in the root zone. Drainage restores that vital exchange. Also, water has a high specific heat, meaning wet soil needs way more heat to warm up than dry soil. Without drainage, this can actually shorten the growing season for winter crops. On top of that, it inhibits anaerobic conditions where compounds reduce to toxic levels, stops valuable nitrates from undergoing denitrification, and ensures vital micronutrients don't get chemically locked away from the plants.
So, based on everything we've covered, it leaves us with a final, provocative thought to ponder. Given the strict physics governing hydraulic conductivity and oxygen flow, without managing the exact mechanics of water drainage, how fast would a saturated environment turn totally toxic and suffocate its own plants? The science clearly shows that managing flow isn't just about moving water around. It is absolutely about engineering the very survival of the ecosystem. Thanks for joining me on this explainer.